Hello, and thank you for joining me for this presentation. Okay, so to begin, I would like you to please imagine with me a place somewhere in the inner solar system where there exists little gravitational influence from any planet or moon, and there is also a near vacuum. Out there in this environment, I want you to imagine a sphere 10 meters in diameter. Okay, now let's cut it in half. Now let's separate the two halves by a kilometer and connect them with material so that they are joined by a large cylinder with a diameter of 10 meters and a length of 1 kilometer. Okay, so this is our spaceship. We have our representation of it here squished down for now. Okay, now let's imagine that the part of our ship inside the cylindrical portion has an interior frame made up of radially arranged metal sheets that connect the outside of the ship to a shaft running down the middle. Let's also imagine that our ship has a special metal part that is connected to the front of the ship. This part has one fluid inlet pipe at the front of our ship, which is then split into several smaller outlet pipes. These smaller pipes run through our heat exchanger and lead to a number of outlets inside the interior of the ship. Okay, now let's imagine that we cut a big circular hole in the back of our craft. Let's say it's a meter in diameter. Let's say that we have a huge tank of liquid water in a cylinder with one hole at the end of it that is connected to the inlet pipe on the heat exchanger in the front of our ship. Let's say that the other side of the cylinder is the front of a piston that we can push so that water is forced through the pipes in our heated part. The liquid water is flash vaporized into a hot steam that rushes in a great gust to fill the vacuum in the spaces between the radial baffling that forms the frame of our ship. This causes the ship to move as a result of the axial surface pressure differential on the interior surfaces of our ship. There is a large amount of steam pressure in the interior of the front of the ship as soon as the water begins to flow through the heat exchanger. Shortly after this, the sides of the craft's interior start experiencing pressure as well. But because these pressures are distributed in a radially symmetrical way, the ship does not move in reaction to these interior surface pressures. They'll cancel out. The vapor will then make its way down to the back of the ship, where it will either bounce against the rear interior surface or exit through the meter in diameter hole. It is only the vapor that hits the back of the ship that we have to worry about. Any vapor pressure on the back surface of the craft will slow us down because it is the differential between the interior surface pressures on the opposite ends of our ship that will provide the propulsion. In this case, the vapor that doesn't immediately exit will bounce around against the baffling that forms the frame of our ship and the rest of the ship's interior until it is either lost as condensation on the interior surfaces or finds its way out the back. Okay, well, how much of the steam would condense on those interior surfaces versus making its way out the back? Let's say that the entire ship is made of steel and that all of the surfaces in the interior of the ship have a network of pipes running through them. Let's imagine that we have a liquid coolant running through our pipes. Now let's check out these three different ship designs. The first has a set of 12 baffles extending radially out from the central shaft. The second does as well, but the baffles are twice as thick, so the larger coolant pipes that we can fit in them can absorb more heat as the steam passes over, and therefore they're able to condense more liquid water out of the vapor before it can escape out the back. The third has 24 baffles, all the same size as the first one. As a result of this, more coolant can circulate through this system as well, so it can absorb more heat than the first one could too. But it also has more surface area for the steam to hit on its way down the channels between the baffles, so it can condense the most of the three. It also has a design that's going to create more turbulence, which I'll get into later. Of the three designs, I think that the top one will get the most acceleration out of the steam generated by the heat exchanger. This is for two main reasons. First is that the extra baffling and the extra condensed water in the bottom two designs add mass to them. The second is that the flow in our fluid in the top example will have a lower Reynolds number than in the lower two examples. A fluid's Reynolds number is used in fluid mechanics to predict the boundaries between laminar and turbulent flow in a fluid system. This is important because turbulence causes resistance to flow through a channel, and this resistance will translate as lost acceleration for our ship. One of the important considerations when determining a flow's Reynolds number is the cross-sectional area of the pipe being used. Since the 12 baffles in our top ship have the most area between them, that ship has the lowest Reynolds number. The channels between the baffles in our second example are only a bit smaller to accommodate the larger baffle sizes, so the Reynolds number for this ship will be a bit higher, but not that much. The channel's cross-sectional areas in the bottom ship, however, are much smaller, less than half the size of the first ship's channels. This will result in an even higher Reynolds number than in the second example, and a more turbulent flow that will generate more resistance. And more turbulence also means more time in the channel and more hits for the vapor molecules against the channel sides, which means more chance for the heat from our vapor to transfer to the coolant liquid cycling through the baffles in the interior of the ship. Other aspects of the geometry of the channel the steam goes through are important as well. If our system had a potbelly in the middle, where the channel is really expanded, then it would also change the flow of our fluid. Perhaps it would help most of our gas go through a phase change in the middle of our ship, or we could start with little baffling and increase it as the steam made its way down the ship's interior, and then get rid of most of it in the middle and repeat this on the other side. But why worry about baffling at all? Well, let's say that the baffling is spiraled, so that as the steam passes over it, it spins the ship, so that as the high pressure, high velocity steam in the front of the ship winds down the channels, it produces rotation, as in a turbine. Now, as the steam condenses into liquid water drops on the surfaces of the ship's interior, the drops will be accelerated away from the axis of rotation around the central shaft, to form a pool of water that jackets the ship's interior. Let's say that with the right kind of spacing and spiraling of our baffling and the right kind of coolant circulating through it, we can design a system that is so good at condensing the steam as it passes by that it condenses virtually all of it into liquid water that flows into the pool. Well, that is what is so exciting about this system. Now we can close the hole at the back of the craft. There will be a small level of vapor pressure on the back of the surface of our craft, but it will be much smaller than the pressure in the end of the ship near where the steam is generated in the heat exchanger. And this is the magic of our ship, the ability to close this system. It has to be quite large because we have to create a large pressure and temperature differential in order to propel our ship forward. And because this takes time, and because the gas is moving toward the back of the ship very rapidly, we need a large amount of distance to accomplish this. When we heat the liquid water in the front of our ship, we are heating a dense liquid, and we can make the heat exchanger as small as we want, basically. This allows the heating and expansion portion of our ship to be relatively tiny. The cooling and condensation portion of our ship, however, must be able to suck this same amount of thermal energy out of this same vapor before it is able to hit the rear of our ship and produce pressure there that will reduce the acceleration that we're trying to get. Because this vapor is moving very fast, and because thermal energy transfer to and from vapors is relatively time-consuming compared to liquids, we need lots of space to do this relatively. Okay, so thus far in our discussion, I have been focusing on the fluid in our system in the vapor phase mainly. When I've been talking about pressure on the different interior surfaces of our ship, for example, I have been focusing on vapor pressure exclusively, but the fluid in our system exists in the liquid phase as well, obviously, and this liquid will be exerting pressures on the interior surfaces of our ship as well. Since it is my ambition to accelerate the ship forward by controlling where there are high versus low pressure regions inside the ship, it would be a good idea to manipulate where the liquid water is applying pressures as well. So what is the liquid doing? Well, let's imagine that we change the shape of our baffles so that the part facing away from the center of rotation ends in these thin little paddle-like extensions. These extensions are intended to keep the liquid in the flow in rotation while still facilitating its flow backwards towards the back of the craft. So let's imagine that we can see one baffle inside the ship and that we are rotating with it so that it seems to be standing still. Now let's say that a drop of water forms from the steam that condenses on the baffle surface. It is accelerated towards the back of the craft as it resists the acceleration of the ship forward, and is accelerated away from the axis rotation of rotation on the baffle as it resists the centripetal force from the baffle surface. In the end, it moves diagonally away from the axis of rotation from our point of view. As it travels further from the axis of rotation, its path will also curve as the amount of centripetal force that it is experiencing increases. Finally, the drop enters a flowing jacket of water that surrounds the baffle system. Now, as I said before, this section only has a few paddle-like extensions to keep the water in it spinning. Aside from that, the goal is to have it flow as freely as possible toward the back of the ship. Okay, but what happens when it finally gets to the back of the ship? Doesn't the water build up in a pool that will exert pressure on the back surface of our craft? Well, sure, but any pressure it exerts will only be as a result of the acceleration of the craft forward, so our craft will still move. Still, though, if we imagine riding on our ship, we would experience an acceleration as the system started, and then we would see this acceleration slowly eaten away as the liquid in our system resisted the flow forward. I know, let's make the system even longer and colder so that as the fluid goes towards the back of the system, it goes from a steam leaving the heat exchanger to a liquid as it condenses on the baffles, and then we'll have a special area in the back where we can freeze the water that flows to the back of the craft before it can reach the back wall. Okay, so now our ship's acceleration from the steam isn't eaten up by a surface pressure from the flow of the liquid as it heads towards the back of the craft. Now let's imagine that we have a little drone that runs on tracks along the baffles, and it is locked to the baffle surfaces, and it has a little unit on the front, like a snowplow, that pushes the ice that collects on the baffles into a little container. And let's say that when it gets to the point where the ice buildup stops, it closes the ice container and stores the snowplow, and then it continues to move forward to the front of the ship, where it empties the container and heads back to the rear of the ship to start the cycle all over again. And let's imagine that we replace our heat exchanger just with like a giant glow plug that generates the same amount of steam as our old heat exchanger by heating these ice piles that our drones are bringing to the front of the craft. Okay, so now we are able to keep our acceleration from the imbalance of surface pressures on the vapor pressures on the back and the front of the ship going indefinitely. As long as we're able to put enough thermal energy into the system at the front with the glow plug end and take enough out with the baffle system in the rest of the ship. Well, that is amazing because there is an abundance of thermal energy from the sun of our solar system. We have as much thermal energy as we need to put into our system's heat exchanger, and we can release as much thermal energy absorbed by the coolant liquid as we want by venting it into space as infrared light. It's kind of hard to predict, just how powerful the propulsion system we could create like this would be. I suppose its acceleration would be something like the acceleration upwards of a hot air balloon. Though, of course, our system is far more massive than a hot air balloon, so this force upward would not induce as much acceleration on our ship as it would on something less massive like a hot air balloon. Still, I'm convinced that this kind of system would be revolutionary. A hot air balloon's thrust might seem small, but remember that I'm talking about using this in areas of the heliosphere where there exists a near vacuum and only tiny external gravitational fields. So check out this webpage from NASA. Their current technology emits ions, and so it eventually does run out of fuel no matter how efficiently it generates the thrust with the amount of mass you have to bring up to do this. Not only that, but the force on the craft from this thrust is equivalent to the force of gravity exerted by a pile of 10 quarters on your hand. That amount of thrust for that massive ship. Still, in its environment, this is a usable amount of thrust because there is little in the way of friction to slow the craft down as it accelerates. The acceleration results in a velocity that increases linearly with the amount of time the engine is running. Well, our craft will be in the same environment, so even though we don't have a huge amount of thrust to work with, the constant acceleration that we are able to achieve will allow us to compete with current systems and do so without running out of fuel. But it gets even better. So let's forget about the ice part and go back to when our ship kept the water in the liquid phase and it was flowing back to form a pool of liquid in the back of our ship that exerted a pressure on the back of the ship that countered the acceleration from the vapor pressure imbalance that was moving us forward. So I have a way for us to move our water back to the front of the ship for recycling in our system that is more efficient than the ice throwing method, and even gets us a little bit of acceleration as well. So it begins by narrowing the back of the craft. Okay, so we'll say that this area extends beyond the end of the old baffling, and that the outside surface here has channels like the baffles. And so the water flowing through these channels is experiencing less and less force, pushing it away from the axis of rotation as it heads toward the back of the craft. And let's also imagine that these channels are spiraled in a way that negates the spinning from the ship almost entirely by the time they end by feeding into a series of pipes. These pipes are spiraled in a way that begins by canceling out the ship's spin as well. The twist of the spiral then changes so that by the time the liquid reaches the other end of the craft, the liquid in that part of the piping is experiencing more centripetal force. And let's say that this part of the piping system is also stretched further out away from the axis of rotation, so that this causes the pipes, or the fluid in those pipes, to experience more centripetal force as well. At the very end of the system, the pipe ends in these nozzles that spray the liquid in a low pressure gas filled environment. In this environment, the spinning jets from the pipes spray against a ring pattern on this front wall. And let's say that this environment is actually replacing that tank in the front of the ship that feeds water into the heat exchanger. So there's a low pressure water vapor layer, and then there is the level of the water in the tank that is feeding into the heat exchanger. And the craft is accelerating forward, and as the water in the tank resists this acceleration, it builds up pressure in the tank. Well, the splashback from the flow out of our water from the jets spraying out of the nozzles in the ends of the pipes is in this environment as well. And let's imagine that the geometry of our ring is such that as the spinning nozzles spray their jets towards it, the flow is splashed back in a pattern that breaks up into a fairly uniformly distributed pattern of mist as it resists the acceleration of the craft through the vapor layer above the level of the water of the tank. And then it runs down the enclosure's walls and into the tank itself. When I was younger, I had a fish tank, which I needed to clean periodically. To do this, I used a flexible plastic tube. The idea was to fill the tube with water. You would then place your hand over one end, and doing so will allow you to lift that end out of the tank and into a bucket below. You were then able to remove your hand from the hose, and as long as the end in the tank was submerged and below the level of the end of the hose outside the tank, water would flow out of the tank and into the bucket, allowing you to use the hose like some sort of aquatic vacuum cleaner on the rocks at the bottom of the tank. The flow rate inside the pipe was determined by the level of the water in the fish tank compared to the level of the end of the tube emptying into the bucket. This distance, also referred to as the system's hydraulic head height, determines the flow rate because it is the tug from the water in this part of the system down towards the Earth's center of gravity that overcomes the water in the tube's resistance to the flow. The water in the U-shaped portion of the system is also experiencing a gravitational pull down, but the pulls from the two opposing sides cancel out. This same principle is what will allow our system to empty the cool liquid back to the front of our system into the pipes. Only we aren't trying to empty a fish tank, we're trying to move our liquid to the front of the ship while that same water resists the acceleration of the ship forward. So let's think about it this way. Let's imagine that I have a hose full of water, and that there are little curves in the ends of the tubes that you can't really see here, but the water doesn't flow out immediately just because the ends are open, right? Now let's imagine that I'm holding the tube, like so, on the bed of a trailer connected to a truck, and we accelerate the truck forward. The water in the hose resists the acceleration of the truck forward and empties out the back of the hose with a flow rate that is largely determined by the acceleration of the truck minus other factors like the resistance of the water to flow through the tube and such. Okay, so now let's imagine we have my fish tank on the bed of a trailer, like so. Now, if the truck is stationary, the water will flow out of the fish tank and into the bucket. And this flow rate will be determined by the height of the hydraulic head between the surface of the water in the tank and the end of the tube emptying into the bucket. If we increase the difference in heights, we get more flow rate through the tube. Okay, so now let's imagine that we have the fish tank set up on the bed of the trailer and we're accelerating the truck. Does the water flow forward? Well, if the force on the water in the tube exerted by the hydraulic head height is greater than the water's resistance to being accelerated forward by the truck, then it will. Okay, so remember that section at the back of the craft where the baffles feed into the pipes? Well, now let's imagine that the channels feed instead into a reservoir. And this reservoir has a hole in the middle for the central shaft to extend out behind it. And let's imagine that this reservoir is split in the front and that there is a set of sealed rotational bearings that separate the halves and that they are spinning against each other. So the water enters the reservoir with no spin from the spiraling of the channels. As it travels down the reservoir, its spin is gradually transferred to the fluid by a spiraled baffled system that feeds into the pipes. And on the other end of the ship, the front, let's imagine that the center shaft running through the heat exchanger extends forward past the part where the ring pattern is located through its center. And let's imagine that there are rings of sealed rotational bearings up here as well. Let's place them where the tank interfaces with the heat exchanger and where the central shaft exits through the ring pattern. Okay, now we can rotate the outside of our system against the inside of our system. We can take energy from the Stirling engine and spin the two halves. We can even put different types of power transmissions from the engines to the different halves so that we could even spin them up to different speeds if we wanted to. We're no longer using the flow of vapor to spin our ship, which gets us more acceleration. We can also control the spin of the outer piping better from where the Stirling engine connects to it around the base of the beginnings of the tubes, and boost the flow through the pipes by spinning them like an Archimedean screw. Okay, so now we have the entire propulsion system. It generates thrust in two main ways. One is by controlling the vapor pressure in the inner portion. The other is by moving the liquid around our system in a flow that meets more resistance moving to the front of the ship than it does to the back. So what do I mean by that? Well, the liquid in the inner portion of our propulsion system is flowing to the back of the craft. And this flow isn't completely unobstructed. Remember, there's those paddle-like extensions for the baffling because they have to go through. But still, the liquid in this part of the system is basically going through one giant pipe and at a relatively low velocity and pressure. Compare that to the liquid going back to the front of the ship in the return circuit tubes. Remember how I discussed the different flow's Reynolds numbers when I was describing the shape of the baffling? Well, Reynolds numbers are actually even better at predicting the characteristics of liquids. Not only that, but the liquid in the inner part travels at least part of its trip down the inner portion as a vapor, while giving us propulsion in that phase. So we have a situation where the fluid in the liquid phase has much more resistance to overcome on its way to the front of the ship than it does on its way to the back. This greater resistance to the flow forward is a net positive force accelerating our ship as well. So our propulsion system will produce constant acceleration for our ship. And it will do so running only on an input of thermal energy, and without producing any exhaust other than thermal energy. This works due to the principle of the conservation of motion. We are harnessing molecular kinetic energy and transferring that kinetic energy to the enormous macrostructure that is our ship. The high-pressure, high-temperature vapor near the heat exchanger transfers more molecular kinetic energy to the ship than the low-temperature, low-pressure vapor in the back. And it is this difference in the transfer of molecular kinetic energy that we measure as a surface pressure imbalance. Likewise, the increased surface interactions between the water and the pipes it flows through on the return circuit create turbulence, which involves an increased amount of molecular kinetic energy transfer compared to the more laminar flow of the liquid through the baffling network. It is in the resistance to the turbulent flow of the water through the outer pipes that we observe the transfer of molecular kinetic energy to the ship in the liquid phase. Thus, both the vapor and the liquid phases of our fluid perform work for us by transferring molecular kinetic energy to the ship in the forms of surface pressure and resistance to flow. And it is this kinetic energy that accelerates our ship forward.